Hello everyone. In this video I'm going to give you a lecture on qualitative inference lines for statically determinate beams. Okay, so first of all, the Muller-Breslau principle states that the inference line for a function is to the same scale as the deflected shape of the beam when the beam is acted upon by the function. So what does this mean? We can explain through these examples here. So if the shape of the inference line for the vertical reaction at A is to be determined, the pin is first replaced by a roller guide. So initially we have a simple of the beam like this, where we have a pin support at A. So if we're interested in the inference line of the support reactions in the vertical direction at A, then we replace the pin support with a roller guide like this, okay, where it can move in the direction of the action of the reactions AY in the vertical direction. So when this roller guide is pushed up by AY, okay, so AY is placed in the positive direction, because in drawing inference line, we take positive for reaction as upward direction. Okay, so when the positive force AY is applied at A, the beam deflects to the dashed position, which represents the general shape of the inference line. So this is a roller support, then it can only rotate, it cannot displace in the vertical direction. So what this force is doing is that you push this bar here upward, okay, and then the deflected shape is indicated by this dashed line here, okay, and this gives you the general shape of the inference line AY, which we have seen in the previous example. Right, so this is for support reactions. Then next we look at the shear. Okay, so for shear, if the shape of the inference line for shear at point C here for this overhanging beam, right, then when we want to determine the inference line, the connection at C may be symbolized by a roller guide. So if we want to look at the shear at C, then we cut across C and then place a roller guide over there, right? And then we apply the positive shear forces, right, at the respective location of the roller guide. So please remember that we are using the positive shear direction as this. Okay, so this is the positive shear force direction that we use. Alright, so when you cut across this section and isolate this part of the free body diagram, okay, then this shear force here is on the left hand side of the element. So on the left hand side of the element, the positive shear force is upward, right? And if we isolate this part of the structure or this bar here as a free body diagram, then the shear across this cut section is on the right hand side of the bar, right? So on the right hand side of the bar, the positive shear force is downward. Okay, so this is the positive shear force downward. Alright, and the action of this pair of shear forces, okay, will cause, let's look at the left hand part of the structure. Okay, let's look at this diagram here. So when this part of the structure or this bar is pushed down by the shear force Vc, and this point can only rotate, it cannot be moved in the vertical direction or horizontal direction. So when you push this part down, the bar will deflect like this, okay, in the dotted line form, right? And then if you look at this bar here, okay, when you apply the shear force Vc, okay, and this point is a roller, so this roller here, it cannot displace, okay, it cannot displace in the vertical direction, so it can only rotate. So when this bar is acted upon by this force here, then this bar will rotate like this in this deflected shape form. So in this case, we can say that the shear force inference line for cross section C here is something like this. Okay, same as the deflected shape acted upon by the function here, BC. Right? Okay, so this is based on the positive direction of shear forces. Right? And then next we want to look at moment, right? So if the shape of the inference line for the moment at C is to be determined, an internal hinge or pin is placed at C. So if we're interested in the bending moment inference line at cross section C here, okay, then we replace point C here with a hinge, alright? And then by applying the positive bending moment, so remember that for bending moment, positive direction, we are taking a deflected element like this as a positive direction, where the bending moment is acting in the indicated direction here. So in this case, this is the positive bending moment sign convention that we use. Okay, so if you cut across section C here and isolate the bar here as a free body diagram, you see that the bending moment is on the right hand side of the cross section. So on the right hand side of the cross section, we have an anti-clockwise moment which is positive for the bending moment. So that is this moment here. And then we look at the bar here on the right hand side here. Okay, so if we cut across section C here, okay, you see that this bending moment here is actually on the left hand side of the cross section. So this bending moment is a clockwise moment, indicating the positive bending moment. Okay, so if this whole bar here, okay, if these two segments of the bar are acted upon by these two moments, okay, then these two moments will actually lift this hinge upward. Okay, and then at the support here, it cannot displace, it can only rotate, as well as at this support here, it can only rotate. So it gives you this deflected shape when this structure here is acted upon by a pair of bending moments like this. Okay, so this deflected shape is the general shape of the inference line for MC, which is bending moment at C. So to prove the previously explained method, okay, so the proof of the Muller-Breslau principle can be established using the principle of virtual work. So before that, we need to know what is work. So work is actually a linear displacement times the force in the direction of displacement, right? So this is work done by a force. If the work is done by moment, then the work is actually the rotational displacement multiplied by the moment in the direction of the displacement. Okay, so if a rigid body is in equilibrium, the sum of all the forces and moments on it must be equal to 0. If the body is given an imaginary or virtual displacement, work done by all these forces and couple moments must also be equal to 0. If the beam shown is given a virtual displacement delta y at the support A, then only AY and unit load do virtual work. Okay, so that is what we have explained there. Okay, alright, so if we apply the support reaction AY at point A here, okay, then this AY will cause a displacement upward. This is del Y, okay, and then if the 1 unit force is placed here, okay, and then this 1 unit force will have a negative work, okay, because the direction of the force is opposite to the direction of the displacement. Okay, so this AY does positive work, but this 1 unit force here does negative work. So the sum of all the work done by the forces in this system that is in equilibrium here has to be equals to 0. Okay, so if del y is equals to 1, okay, then we get AY equals to del y prime. Okay, so the value of AY represents the ordinate of the inference line at the position of the unit load, where AY is equals to del y prime. Okay, so when this 1 unit load is placed at this location here, then the reaction at AY is given by this ordinate here, as we have seen in the previous example. And then as for shear, okay, so if the beam is sectioned at C, okay, the beam undergoes a virtual displacement del y, then only the internal shear at C and the unit load do work. Okay, so these are the directions of positive shear. Okay, so the shear on this side is going up, the shear on this side is going down. Okay, and then if the 1 unit load is here, then the deflected shape due to the action of this pair of shear forces will be something like this, which indicate the inference line shape. Alright, and then the displacement due to this pair of shear here is del y. Okay, so if we take this point as the reference point, okay, then the total displacement is del y. Okay, so this is the work done by VC. Okay, actually this VC caused this much of displacement, and this VC here caused this much of displacement, which are all positive work done by the shear forces. Right, and then for this 1 unit force here, the direction is opposite to the displacement. Okay, so this 1 unit force does negative work. So the 1 unit force does negative work, and then the shear force does positive work. Okay, and then for equilibrium, all the work done by the forces should be equals to 0. Okay, so if del y is equals to 1, then VC is equals to del y prime. So in this case also, if we want to know what is the shear force at C when 1 unit force is placed over here, then the ordinate here gives you the shear force at C. Okay, so that's the proof for the shear force using the Muller-Breslau principle. And as for bending moment, okay, if a virtual rotation del phi is introduced at the pin, virtual work will be done only by the internal moment and unit load. No? So as we have seen just now, we replace point C with a pin, right? And then put in the positive bending moment, and then this positive bending moment will cause the beam to deflect in this manner, okay? And then for this bending moment, they cause a rotation of del phi, yeah? Okay? So if the 1 unit force is here, then this is the displacement for this 1 unit force, which is in the opposite direction of the 1 unit force. So this 1 unit force also does negative work. And then the work done by this pair of bending moment is mc times del phi, right? So the moment does positive work, and then the 1 unit force does negative work. And then the total work done is 0 for equilibrium. Okay, so if del y is equals to 1, then mc will be equals to del y prime. So in this case, if the 1 unit force is here, then the ordinate of the inference line will represent mc, okay, as indicated here. Okay, so in this case, for each beam, we need to sketch the inference line for the vertical reaction at A. So let's take a look at this first example here. So the vertical reaction at A is at this pin here. So for reaction, we replace the pin with a roller guide. Okay, and then we put the reaction in the positive direction that is upward and see what is the deflected shape of this bar here. Okay, so you see that this, when this bar is acted upon by a force there, okay, then this bar will deflect in this manner. So this will give you the shape of the inference line for AY. Okay, and then for this example here, support A is here. So now we replace support A with a roller guide and then apply AY in the positive direction. And you can see that this is a hinge here. So if you apply a force here, then this bar will deflect in the dotted line like this, okay, where the hinge can rotate, okay, and this roller here also can rotate, but it cannot be displaced. And then this pin support here can rotate but cannot be displaced in the vertical direction also, so it will rotate like this. So this gives you the general shape of the inference line for AY in this particular beam here. Right? And then as for vertical reaction at cantilever beam, okay, so first of all, if you want to know what is support reaction inference line for point A here, okay, so replace this point with a roller guide, but this beam here initially it is a fixed support, okay, so we only release the vertical direction, okay, the moment resistance is still there, so this bar cannot bend, right, because there is a moment of resistance. Alright, so this bar can only slide in the vertical direction. So if we act upon this bar here with a roller guide at A, that we have released the reaction in the vertical direction, and we put a reaction force AY, okay, on the roller guide, then this whole bar will actually move upward, okay. So this will give you the shape of the inference line, okay, in which AY is a constant across the X direction. So that's all for the lecture. Thank you very much for watching.